Hello, I'm Aalok Kafle, and in this video, I will be talking about time series forecasting and especially about uh, building a LSTM model uh, for time series forecasting by using Keras and TensorFlow. So the data I'm going to use here to build the model time series forecasting is J17 well index, which is basically a well located in San Antonio, Texas, as you can see on this Google capture here. It was drilled back in 1983 and it is around nearly 800 feet deep underneath this ground, and it's measuring water level changes in Edwards aquifer since uh, early 1930s, and we have the data running still now going. We get the data every day. So this is the location of where the well is, and this is the source of the data for what I got the historical data of the water level in the wells from. So I'm trying to build a long short-term memory network, which is basically a recurrent neural network which is able to handle time series data. So something that happens in a continuous sequence. So the ability with it is it can capture pattern in the time series data so that we can use it to make predictions for any sort of future data. So the name long short, so it is used so that it has two types of memory. One is called long-term memory and one is short-term memory. So long-term memory is being stored as a model where we are providing the data. It builds a trend over time and tries to capture those properties. And short-term memory is something, to predict a time series data, we provide a lag of the time series, basically being to predict a value on the nth day. We give n minus 1, n minus 2, n minus 3, n minus 4 as an input. So that it makes itself usable as a short-term memory. So it's being updated frequently at each and every iteration. So just like I said, number of neuron, that is time lagged input, is a controlling factor for the short-term memory. So how many lagging times do you want to give as an input to predict the data on the nth time? So that is some sort of decision we have to make, so that we don't give too much, so that it will start hampering or capturing the long-term trends, but we don't want to give too little so that it doesn't have any short-term trends. So finding the right position. So for building an LSTM model, one of the most important things we have to do is while splitting the data into training, validation, and test split, it's not randomly sampled like any other sort of neural network models. Here it will be a temporally ordered splitting. So the main idea here is model is never trained on the data from the future. So basically, we have to train the data on the data from the past and use the data beyond that point. So training data should be the one that occurred first in the time series, and testing data and validation data should be following the training data. So in our data, in the data I just talked about, J17 world, we have the data from 1932 to 2023. So I split the time series data into training, validation, and testing with 80-10-10 split. So 1932 to 2004 I'm using as a training data, 2004 to 2014 I'm using as a validation data, and from that point forward to 2023 March I'm using it as a testing data. So after splitting this as a 3 screens on a single graph, let me talk about the model architecture I'll be building to build this LSTM model. So the first thing I'm trying here is I'm building an endogenous model. So while building the endogenous model for the output variable or the lagging input variables, I'm using a 10-day rolling average of the well so that it kind of smoothens out any large spikes or downfalls. And for the endogenous model, of course, there will be no other external variables, so only the lagging time of the same variable, the water level, will be used as an input. So I'm using 5 lag values. I'll be sending 5 days of data to predict 6th data, basically. And about the actual model architecture, I have after I have the input layer of 5 nodes, 5 neurons. The second thing I have is 128 neurons LSTM model, and after that I have one more dense layer with 8 neuron, which has a radio activation function, and of course the output layer, which is giving me a single value as a predicted value. So this is the model architecture. I've shown a short snippet here. So some other things I had to choose here is the optimizer I'm using is Adam with a learning rate of 10 to the power minus 5, and I'm using root mean square as the loss and metrics while building the model, and I'm using 10 epochs while training the model. So the results after training the model, this is the result I got for training data. So if we see here, so on this overall all the data of the training, it looks very similar, and when I zoomed in into a certain portion of this data, so it's saying that the predicted values are being slightly smaller than the actual. Only for this time frame, it is not same across all the data though. So you can see some values are higher here and some values are lower here. And if I do a x equals to y plot, being actuals in a y-axis, actual data in the y-axis and predicted value on the x-axis, this is the plot I got. We can see it is everything is very close to the x equals to y line. So the next thing I did, I used the same model I built for training the data for testing the data. Of course, validation is also used while training the data and getting the best parameters. So the result I got for validation were also very similar to training data, and testing data, although in terms of RMSE performed slightly less better than validation or training data, it is still performing very good if we look across this plot, and everything is very close to this x equals to y line. So endogenous model is performing well by giving 5 lag variables here. And next thing is I repeated the same thing for Komal Springs flow. So this is a discharge data for the Komal Springs, that is a slight downstream of it. So the time period when it's available was different, but other than that, I use the same principle, same model architecture, 80-10-10 split, and you can see on the training data, it's performing very good with everything very close to x equals to y with some outliers here. And same thing in the validation and testing data. On validation, it's trying to get the best hyperparameters here, and it is being able to capture the trend, although not exactly follow, like trends are being captured very well here. And same thing on the testing data. And again, I repeated the same thing for San Marcos flow as well. The only different thing here is different time period, and other than that, everything is same. Same model architecture, and it is also being able to capture the trends. And same thing applies for the validation data and testing data for it as well. So at the end, I also tried exogenous model by downloading the temperature and precipitation data from 1981 to 2023 from Prism data. And by doing that, I provided 5 lag variables of both temperature and rolling sum of precipitation. And by performing it, the exogenous model, by just providing 2 different variables to predict the water level elevation, was not doing well, and it was just trying to, it wasn't even able to capture the trend. But I repeated the same thing again by providing water level elevation as 1 extra variable. So I'm providing water level elevation, rolling sum of precipitation, and temperature as inputs, and 5 lags of each variable. And here what I can see is it is being able to capture the trend, although not exactly very closely match. It's at least being able to capture the trends here. So this is the training part and this is the testing part for 80-20 split. So we can see it being able to sort of capture the trend going down up exactly as the actual data, but not matching very much. So to summarize, we use the LSTM model using the sequential TensorFlow So something that was different was just the way the training and testing data were to be arranged in the beginning, because we needed a lag variable. So we had to create a function to just arrange that in a matrix format so that we could give it to the LSTM model. And endogenous model obviously performed better than the exogenous model, as I stated earlier. Thank you.